Okay, so after let's say a very elementary introduction about neural networks, so in this course we are touching very different topics in a few slides. So now I want to try to give you an idea of another topic which is important in electronics, but not only in electronics, because it's an application of electronics which is important in many different fields, which is something about digital signal processing. So far we have seen something about analog signal processing, which basically means all the stuff of the Fourier transforms, filters, amplifications, and whatever. But nowadays we make use of digital signals, so we need to represent an analog signal into a digital way. And why we need this? We already anticipated this thing when we were speaking about the history of the computers. So with the analog signal there is the problem of the noise. So the signal can be corrected by noise. Of course we can put filters, but filters are not perfect. Then a single mistake in one level of analog voltage can lead to a very big error, so the error propagates, so it can be done, but it's not very convenient. So now the idea is to transform an analog signal into a digital number. So let's speak about the first circuit which is useful to that purpose, which is the so-called digital comparator. So here we have something that we might recognize. So we have this circuit, we have two resistors connected this way, and they build a so-called voltage divider. So they are powered up by plus 5 volts here is ground, and so we can easily write the voltage here, I call it V plus, because later it has been applied to the positive input of an operational amplifier, and V plus is VCC, so this thing I call it VCC, multiplied R2 over R1 plus R2. So if I choose 1 kilo ohm and 1 kilo ohm here, just to make an exercise, let's try to calculate. So we have to calculate this coefficient. It's very easy because it's 1000 divided 1000 plus 1000, and this of course makes 0.5. So VCC is 5 volts, and therefore 0.5 multiplied 5 volts is 2.5 volts. So here V plus is 2.5 volts. This node is at 2.5 volts. So this thing is attached to the input of an operational amplifier. We know that the input impedance of an operational amplifier is close to infinitive, I mean, close to infinity doesn't mean anything. It's very high. And so we can assume that no current basically is entering here, which basically means that an hypothetical resistor, so-called parasitic resistor, that might be present here or somewhere else, I mean, this resistor is very, 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 very big. And if we put a resistor in parallel to something else, and this resistor is very big, it's like if this is not existing. So this V plus voltage is not affected by the presence of this operational amplifier. This is the end of the story. But now this operational amplifier has another input, which now is connected to a sinusoidal source of voltage. So it's this. The signal might go down, up, down, up, down, up at this input, the V minus. But the V plus is 2.5 volts all the time. Then we know that the operational amplifier has a certain coefficient of amplification A, which is very big. It's the open loop amplification factor. So I'm speaking of this thing. Where was it? Here. So the model for an ideal amplifier was that the open loop gain was very high. By open loop gain, I remember you, is the gain of the amplifier without any feedback connection. So we are not speaking of G here, we are speaking of A. And we can realize that here in this circuit we don't have feedback connections. So the equation of this thing is that the output, let's call it V output, would be equal to the difference between V plus and V minus. So let's call X minus, sorry. Okay, I put it in the input plus, doesn't matter, minus X is inverted, plus 2.5 volts. So we can call this delta X if you prefer, multiplied the open loop gain A. So if this delta X is positive, then the output is that number multiplied the huge number. So let's say it tends to go to infinity, but we know that it will be clipped, because once it will reach the level of the power supply, it cannot produce an output which is bigger than that one, and vice versa. If this thing is negative, which means that this is X is less than the threshold. And here we have this behavior described like this. So the output is a binary output. It can be either high or low. So we say 1 or 0 in the logic meaning, according to a threshold that we set here. So this is one way we can implement a thresholding mechanism in electronics. We have an amplifier with a very high gain. The amplifier is saturated because the output cannot surpass the voltage that powers up this device, and with the voltage divider we set an input at this differential amplifier. So why do we need this? Well, we need this for many things, but you can imagine, for instance, that you can do one thing. If you put an input like this, so let me switch to the blackboard. So let's say you have a variable x, which is analog, so it can be any function of time. You put this thing into a comparator. I put this symbol for the comparator, and let's say you have a certain threshold t0, then this will give you an answer which is this. Is x bigger than t0? Then you can put the same input simultaneously to many comparators, like this. For instance, here, 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 here. All of them with different thresholds. And each of them will answer this question. Is x bigger than the threshold, let's say the threshold Tn? So now imagine that I create a set of thresholds which is like this, spanning a range. Like I put the first threshold at let's say 0.1 volts, the second threshold at 0.2 volts, the third threshold at 0.3 volts, and so on, let's say to 5.0 volts. And now it's easy to have a binary representation of this signal, because if the signal is if all those outputs are 0, it means that for sure the signal is 0, or let's say it's below the first threshold. If the signal reaches a point for which it surpasses this threshold, this, but not all the others, it means that the signal now is at this level. So this binary representation, in this case 1, 1, 1, and then 0, 0, 0, 0, 0, will describe my signal. The more the signal is high, the more ones I have in this output vector here. So I can create a code, that binary code that represents my analog signal in a digital way. So those type of circuits exist. They are called analog to digital converters, and this type of implementation is called flash implementation. It's called flash because it's the fastest possible implementation of an analog to digital converter. It's very fast because this threshold is a very easy operation to be implemented in hardware. We can have very fast amplifiers, threshold amplifiers, and the interesting thing is that all those amplifiers are all working in parallel, because the input is split simultaneously to all of them, and so we don't have to wait so much time. So if one is done, all the others will be done simultaneously. So this technology is important if you want to be able to convert a signal from analog to digital in a very fast way, but there is a cost, there is a catch that we have to pay. The thing is that we need so many of them, one per each level of voltage we want to convert. So for instance, if we want to create a signal which is divided into 8 bits of information, it means that we need 2 to the 8 levels, which is 256 possible levels, which means that we need 226 circuits like this, which is a lot. And still these 8 bits would be called 1 byte. It's a lot, but not so much, because nowadays we are used to represent numbers, for instance, as float numbers, which takes into account 4 bytes, or sometimes let's say they are called float numbers, or sometimes also 8 bytes, which are called double floats numbers. And so, for instance, if we want to have all 8 bytes, it means that they are 8 by 8 is 64 bits, and 2 raised to the 64 is a very big number. So imagine how many comparators you need. So at a certain point, basically beyond 8 or 10 bits, this technology is not very viable. So sometimes we need to find other methods in order to convert signals from analog to digital. Okay.